Good morning, everyone, and this is the John Chappell Natural Philosophy Society Science Chat. And I am your host, Franklin Hu. So it's been a while since I've been on. David has been great in presenting a number of interesting speakers over the past month or so, but I saw that nothing was scheduled for this week. So I'm guessing I'm back in the hot seat in doing the moderation for the science chat. So we're going to get back to general science chatting. So if you would like to join me in a live discussion, you can do that. And you just need to go to, let's see here. We have that in our banner here, I thought. Let's see here. You just need to go to live.naturalphilosophy.org to join the live stream. And our green room can hold up to 10 people. So currently I don't see anybody in the green room, but if you have any questions, also, I see we have 5 viewers out viewing us on either YouTube or Facebook. Welcome. And we're just getting started here, but if you would like to actually join discussion, you can either go to live.naturalphilosophy.org if you're not camera shy, but you can also always enter comments. Like you're in YouTube, if you add a comment, if you have a question, I will usually immediately see that and can try and address that. Okay, so enough with the preliminaries here. So today's topic, we're going to be delving into the question of what is the shape of a photon? So that is the question of the day. So I'm not going to dilly-dally around. I'm going to tell you the shape of a photon is a rod. Okay? So if you were to draw a photon somehow, I think you'd come up with something like this. Okay, it's just like a pencil, right? Or like a ruler. Or like a pen. Okay, so you might think that's crazy, but I'm going to have to explain. So first of all, I mean, it's not clear that a photon even has a shape or, even what it is. But I believe that as a physicalist, I mean, I like to see everything represented in an actual mechanical, physical sense. If you cannot show it on a billiard table, then I would, generally speaking, not believe you. But, I could see putting a pen on a billiard table or lining up 5 balls on the billiard table to see that that is a rod shape. And as a physicalist, we've had these kind of problems before. For example, I would cite the shape of the DNA molecule. And looking at the history of how that went, it's like people knew what components actually made up the DNA. They do the nucleic acids, and they had all kinds of different formats for that, but no one came up with the actual shape, and they were working on it for quite some time until someone came and discovered, oh, we can put this in a helix, which twists around, right? That matched all of the experimental data for how the DNA molecule was actually shaped, right? So in the same way, I think that we need to get the discussion to a point where it is a completely physical thing that we can draw a picture of, that we can get the handle of, and not this kind of like mysterious speak of photon without knowing what it is, right? So let's see, we have some comments here. Okay, let's see here. From Espacio, he says it must be a hexagonal mass. As far as the photon shape, I'd be curious if you think that it is hexagonal, and why would that be? So you also have to comment as what is, let's see here, what is up is down. See in the supernovas how hexagonal is in there. See in how air makes snowflakes. And we also have a comment from Bill Lucas, who's asking an electrical engineer how photons are processed by antennas, and they will tell you about the shape of a photon. Well, I would be curious exactly, because I've never heard any electrical engineers tell me what the shape of a photon is either. You know, I am putting a line in the sand, and I'm saying that the shape of a photon is in fact a rod. It's not a complex thing. It's not a vortex. It's not a torus. It's in the shape of a rod. Although that brings us to the question: is it a literal rod? Is it literally like a pen that's solid? And to that, I would say no. I would say that strictly speaking, that light is in fact only a wave phenomenon. So I'm going to put my banner on that. Okay, not only is it a rod, but it is a, oops, let's see here. Where's my banner? Yes, if you want to go and okay, so why would I say that light is a wave? Okay, because there's a big controversy over just that. Because we have all this light wave duality thing, and the last time I mentioned it, I think they said, well, a way to ignore the light wave duality. And I said, yeah, I'm not ignoring it. I'm saying that that's wrong. That light is not a particle in a sense like an electron is a particle. So in that sense, if I'm saying that light is a wave and the light is in the shape of a rod, then what do I mean by that? Okay, because that's not a wave. Okay. So what I mean is that if you were to take, for example, a wave pool, you've seen these. They will like dip a probe into the water, and you will see the waves spread out through the wave tank, right? Now, what I would think is that if you had a wave tank and it was, say, very narrow, and you dipped a rectangular type thing in there, that would generate a single pulse wave that kind of traveled down the track. Okay. Now, each individual wave is in what I would say the shape of a rod. Okay. So that's what I mean by light is a wave and it's in the shape of a rod. Okay. In that it is constricted. It has a fixed, it does have a fixed width. No, it has a fixed width, right? It's not actually a rod. If I could draw this, I mean, it's kind of hard to draw waves, the problem. But it has a fixed width, it has a fixed height and amplitude, and it travels basically in a straight line, okay? So that is part two. It's kind of, I would say, a wavelet. Now, normally we don't see these kinds of waves in, the normal world, because if you, like in a wave pool, we create very large circular waves. We don't see like a 3-inch wide wave just kind of traveling on its own, right? Because if you tried to do that, it would quickly still spread out into this big circular thing. But one of the other characteristics that light has is that it actually doesn't spread. So it's as if, I had my wave pool and I dipped the pen in, and it only created a wave the width of the pen that traveled down to the opposite end of the wave tank. Like I said, we don't really observe that kind of behavior in substances like water, which have frictional losses and are dispersive. So the photon does have kind of this special property that we can't really see in ordinary compressive mediums, in that it really doesn't, it doesn't have to spread. Although in many cases, it does spread out in the same kind of circular way. And that brings up the question of, if light is a wave, then, the obvious question is, what is it waving in? Let's see, we've got some comments here. Let's go over, which is the exact, whatever waves has to be something. I'm not exactly sure what that means. Let's see here. Anything, even light, must have mass, since is a thing we see and somehow waves. Well, it's like that would be the same kind of question of, does a wave in water have mass, right? And definitely the waves can impact things and move them around. So in that sense, the wave does have mass, I would say. Let's see here. Let's see. Did I ever see that? Says a quanta cannot travel in straight line in a cubic lattice. Well, maybe and maybe not. I think we'll have to do that. Let's see here. I can't seem to enter the live room. Just gives me expired. Yeah, I was afraid of that. We keep on having problems like that. So Ian, I did put in the, let's see here. Okay. So if you're having trouble getting into the live room, try this link. Because somehow it always associates that live.naturalphilosophy.org, it was sometimes, to an old and expired link. And since David normally sets these things up, but I had to kind of set it up myself. So maybe I didn't quite get the link right. But Ian, if you can join me in the live room, that would be great. Let's see here. Not a thing may go always straight to me. It's possible, but like I said, this is one of the characteristics. If you're going to explain anything about light, you kind of have to explain, why does it travel in rays? Why does it appear to travel always completely straightly, generally speaking? And why is it, it's very localizable, right? That's one reason that I think it has to have a physical shape, because definitely, like in, say, with the case of gamma rays, like if a positron and electron slam into each other, they generate two back-to-back gamma rays, and those gamma rays don't hit all over their detectors. They go and they hit a specific spot in one of the silicon detectors, and you can see it hit there. And then there's another one that hits in 180 degrees in the other direction. We don't see a gigantic, I don't know, spreading wave or anything. We see something which looks very, particle-like. And that is another reason why I think that a photon is in the shape of a rod, which is localized. So we don't see it always spreading out. It is particle-like in that sense. It has finite dimensions. It can only hit something once, and it travels in a straight line, right? These are the three characteristics of a photon that we have to account for, and I think a rod accounts for all of those properties. Now, probably the trickiest property of a photon is probably polarization. And this talk itself is kind of an outshoot of discussions that I've had with Draft Science. So I have like one of his links here. For example, we have Draft Science on polarization. And let's see, I'm going to share my screen, and we'll just play his video here for a moment so you can kind of see what he was proposing here. Okay, so that's a small sample of Draft Science. And his idea of a photon is that it is this clump, right? Now, I don't necessarily disagree with that because, my rod, is a form of clump, right? But what Gary doesn't recognize is that light is a wave. He thinks that light is very much like a particle. And that means that it doesn't require a quote unquote medium to go from point A to point B, right? Whatever his photon is, it can travel through completely void space. And it's not a wave, okay? And that's a very popular viewpoint. And he could say things that the frequency is due to the quantity of these clumps per second hitting anything, right? So that just means that higher frequency means more clumps per second, versus the wave idea, which is that you just have a medium which is compressing and rarefying and compressing and rarefying. And the frequency is dependent upon how fast that happens, right? So one of the interesting predictions of, say, this versus that theory is that the Draft Science would predict that light waves would not, if you could measure them, would not come in sinusoidal, would not be measurable sinusoidal. I mean, basically, you'd see, it would hit, right? It would be kind of like a square wave that, bang, bang, bang. You'd see either the amplitude would either be 100% or zero, versus a wave interpretation, which you would see always gradual rise to the maximum amplitude and dropping down to 0. So that is a possibility, and he challenged me to prove that electromagnetic radiation comes in these sinusoidal things, right? And so all I would need to do is to come up with an experiment that generates, say, a radio wave as sinusoidal, or as square wave, or triangle wave, or some other specific kind of shape that requires variable amplitude. And curiously enough, I really couldn't find any such experiment. You'd think it'd be relatively simple to do. I've been tempted to do it myself, to just create a square wave, transmit it with the simplest radio transmitter I can make, and then connect it to an oscilloscope with the radio antenna and see whether I recover the square wave or the triangle wave or the sine wave. And Gary is saying that you would not be able to recover anything that looked like what you transmitted. It would probably all look sinusoidal, no matter what you transmitted. But like I said, Gary kind of got me on that, and then I don't have that specific experiment, but people think that that's what would happen versus a particle, that it's always going to be an increase in the density versus the not density as a wave. So Gary, if you're watching, he normally watches that, this is for you. So I am disagreeing with that particular idea of what an electron is, right? It is a clump, but it is a wave, right? Like I said, the closest analogy I can have is that you have a very narrow trough and you generate a wave. In one end of it, you see a very narrow straight wave run down that trough. And that is what I'm saying a photon is, right? It is not a particle in like the sense it's has mass, or it actually moves from point A to point B, physically moves from point A to point B. It is something which is transmitted through a medium which stays in place. And I think that's important because one of the characteristics of light is that it can travel like virtually forever, right? Long distances, super long distances. And it does so super fast. And we know that waves can do that versus, particles. Like if I had a swimming pool and I was trying to shoot a BB through the water, it would not get very far. It certainly would not hit the end of the pool, and it certainly wouldn't go very fast. But if I put a speaker under the water and I started playing, say, music, then yeah, you could probably hear that sound being created by the waves all the way at the other end of the Olympic swimming pool, and it would travel extremely fast, right? So this is why I think that the light must be strictly wave phenomenon. Although that does bring up, I was bringing up the question of, well, if it's waving, then it must be waving in something, right? So that's the other. Let's see, you're saying that the video was lost in the sound, and that's probably the case, because usually when you play videos, it usually does not transmit the audio. But yeah, you could kind of see that he was kind of drawing his clumps anyways. So we do have another comment here. It says maybe 2 gamma rays are similar to the jets that shoot out of galaxy centers along their axis of rotation. Well, could be, except that I think galaxies are a little bit more complicated than electrons and positrons. So let's see here. A light source is visible from all directions, so particle explanation fails there. Well, no, not strictly. That's why I was saying the example of positron, electron generating gamma rays, and that the light source, in fact, is not visible everywhere. It's only visible in two little spots. But if you put a candle in the middle of the room, that thing is generating so many of these light packets that that is visible everywhere. So, and we have things like lasers where, you can shoot a laser, it will go exactly where you point it, and no one can actually see the laser as it's going through space, not unless it hits something like a dust particle or something. So I'm thinking that it can still kind of act like a particle. Although your point here is that the particle explanation fails because of that, but actually it doesn't. Because really, it's not unreasonable to think that light is a particle because, if it looks like a duck, quacks like a duck, it's a duck because of the properties I named, which is that it travels straight, it doesn't disperse, and it appears to hit its target like a bullet, right? Generally speaking, we don't think waves do any of those things, but I'm saying that if it's in the shape of a rod, that it will in fact do that sort of thing. Let's see, we have some other comments. A resonating source generates a continuum wave. It requires a forcing function to replace the energy radiated. Well, generally speaking, I would say yes. Any energy that is being emitted by something does take an energy source. So I think we'll discuss that in the question of how a photon is generated. Why not see a circle in matter as water here in Earth? I'm not quite sure I understand that. The super long distance travel of light is baffling because of the inverse square law. And I think that the way that works is that the inverse square law only works in the sense that, like, you have a candle and it's emitting, billions of these photons. And then if you look at how many of those photons hit any spherical surface heading away, that is what they mean by the 1 over r squared law, in that density gets lower. But for any individual photon, its strength does not decrease. That a photon emitted from Alpha Centauri comes in at full amplitude when it hits the Earth. It's just that by the time it gets to the Earth, all the other photons from Alpha Centauri have been diluted over the 1 over r squared range. But curiously enough, it's like a bullet that doesn't slow down. The actual individual photon itself does not obey 1 over r squared. It travels like through space, as I've been saying, like a rod, in that sense, it is bullet-like. This is how I try and solve this question of, is it a particle because it's got all these particle properties, or is it a wave, right? And I say it's a wave that has these particle properties. And a rod satisfies all of those 3 observed properties. But it's still a wave, right? So matter state, stars made of plasma, hot light and cold light. Possibly. Good point in the coherent light thing, it doesn't spread as an expanding sphere. That's right, it doesn't, and that's one of the things which is, like I say, not terribly intuitive if you think about waves, because there's almost no such thing as a non-dispersive, laser-like, say, sound wave, I would guess. But in some ways, you have to kind of say that is what's really going on here. we have a comment from, see here, comment here. You can't say not wave or not particle since each is just a way to represent observed data, not an account of the underlying physics. Well, here I would disagree. I would say that physically, if you could take a picture of it, that strictly it is wave phenomenon. So I would say that it's not that you're right, it's a matter of observation, but in the end it has to be something, right? So I would say that you have to think of it as a compression medium. Now let's see here. Now I'm going to get to what the most complicated aspects of the photon is. I mean, we've discussed three of them, which is that it has all these particle-like phenomenon. But one phenomenon that is difficult to explain is the phenomenon of polarization. So that's why I brought up draft science explanation of polarization. And yeah, this is one of the main motivations for why I believe that light has to be in the shape of a rod. Now, in conventional physics, they say that a light wave consists of a magnetic field and an electric field running at 90 degrees to each other in phase. Okay, so the way they explain polarization is like a rope through a picket fence, right? So you have your picket fence and you wave your rope around, and the only wave that it's going to accept is the one which lines up with the picket fence. And so the picture of the conventional electromagnetic wave fits through those slots and only allows, the polarization that aligns with the slot. And, that is another picture of the photon, which I disagree with. I mean, just to compare, okay, if I'm saying photon shape of a rod, right? Conventional physics saying photon is this wave at 90 degrees to each other. It has magnetic and electrical components in it, right? I mean, that's not even really a shape. That would be an example of a photon which is represented by just literally changes in the field strength of the magnetic and electric field. But you kind of ask, like, well, like, how big is it? How high is it? I mean, it's not even big or high. It's just that if you stuck a magnetic meter in space, you would, as a photon goes zipping by, you should see it like increase and then decrease and go negative. And if you were to measure the vector direction of the electric field, you would see it pointing this way, and you see the magnetic field pointing that way if you had a magnetic and electric detector. So that's very different than what I'm saying. I'm saying that light is a compression wave, right? Has nothing to do with either electric or magnetic fields, right? Now, this is a big departure, right? This is where most of the mainstream scientists would leave me. They're saying, what? You're saying electromagnetic wave has no electric and no magnetic fields? And I would say, yes. And I've been arguing this a lot on the internet, saying that if that were true, then show me the experiment where when I see a traveling photon or radio wave, show me that you put your magnetic detector in the path of that radio wave, and show me the increasing and decreasing magnetic field, and show me the increasing and decreasing electric field, and show me that they are at 90 degrees to each other. Now, experimentally, we have instruments that could do that. We have instruments which are only sensitive to electric fields and have instruments which are only sensitive to magnetic fields. And they're very modern, and it's we should be able to do it. In fact, I should challenge some university professor to perform that experiment, because no one seems to have even attempted to prove the very basis of the mainstream idea of a electromagnetic wave, and especially these planes that are supposed to get polarized. So why do we believe in something that has absolutely no experimental support? I mean, plus you have to deal with this thing about you've got these disembodied electric fields, which are normally have to be generated by present charges, right? Or magnetic fields that normally have to be generated by, say, permanent magnets. And you've got none of that in blank space, right? So, and then somehow you're supposed to say that the increasing magnetic field is then creating the magnetic field, and then the magnetic field is creating the electric field, and it's like, yeah, if you look at the math and Maxwell's equations, it's like it could work out that way. You know, it's not an unreasonable theory, but theories you need to be able to actually experimentally prove, right? So if you cannot show me the separate electric and magnetic field components, then you have not proven your point. I mean, all you have is just equations on a blackboard. And equations can be, you can make anything equal to anything. You can say apple equals orange, and it looks perfectly fine. Except when you get an apple and orange, you see that they are not equal. But if you if you do that, then it's kind of like garbage in, garbage out. So that's an important point, that there's no actual electric and magnetic fields in a photon. But what about this whole polarization thing? So if it's not the rope through the picket fence, then what is it? I mean, definitely there is something about light which can be filtered, right? You take your polarization filter, we use these in our movie theaters, and wear our 3D glasses. There is something that, if I twist the polarization filter one way, the light definitely contains some component which can be filtered on an angle. And that is why I say that it must be a rod, and it must be traveling in, say, this direction, like towards you. And what the polarization is going to be the angle that this rod is oriented, right? So if it's coming at you, that is one polarization. So if I have a rod and it's coming to you at this polarization, and I have a filter that blocks everything that, I don't know, goes like this way or that way. Now, if it's going to do that, then it's going to come, it will completely block all of the light rods which are coming in this direction. But if my polarization is in the same direction as my light rod, then it will allow it to pass, right? So very important, and this is actually almost entirely why I think it has to have some physical length in order to encode this polarization, right? That is the key, and this is a relatively recent discussion based upon polarization, because even myself, I wasn't quite sure what the shape of a photon would be. Maybe it's just a big circular thing. These are the other possibilities, maybe it's a square thing. But in order to encode polarization, it has to basically have some kind of dimension in the transverse direction, right? Wave travels this way. There has to be something in the side to side transverse dimension to encode which way this thing is pointing. Now, another way to think about this is how basically radio waves work. And the way that radio waves work is that in order to build the best possible radio transmitter and receiver, your antennas should be oriented in the same direction. So if I have like this, like my pens, my two pens here, that the best way to receive the transmitter is to have them in the same direction. If it's in 90 degrees like this is very, very bad. Okay, the receiver will not be able to receive much of what is being transmitted just by the orientation of the antenna. Okay, now if you think of this as like rod-like things coming off the transmitter, right? That if the rod-like thing hits the rod, it's in the same direction, it's going to hit the entire uh, length of the receiver, right? So you can get very strong signal. But if you have a rod and it's coming along and it hits at 90 degrees, then only, very, very tiny bit of the wave is going to intercept the receiver, right? So this is not going to be received very well, okay? So that is actually the true reason for why polarization occurs, all right? But this does bring along another, I would say, major difference, which is the difference between radio waves and photons. So I would categorize those things as two completely different things. Okay, now they're both still compression waves, right? Having nothing to do with electric or magnetic fields, right? But the difference is that photons are quantized, meaning that each photon only contains a fixed amount of energy, versus radio waves, which can contain, I would say, variable amounts of energy. And radio waves and photons are generated in very different ways. So photons are, like light, is generated by, I would call, atomic processes, where you have electrons and they are moving in the presence of atoms. And in that process, they generate photons, individual light packets. Versus a radio antenna. A radio antenna is very easy to make. You just take a metal rod and you apply a voltage to the base. And you just vary that voltage and magically waves appear, right? And the way that I feel that works is that it's basically the same thing as if you were in a wave tank. You dip the object into the wave tank and it generates waves. And if I dip my pen in the middle of like a bathtub, you would see the wave would take the shape of the pen. And it would have very long waves going this way and little short waves going out that way. And that's actually in radio engineer speak, that is the radiating pattern. The antenna radiates the waves basically in the shape of the antenna, right? And so radio engineers have to take that into account. That's what's happening. It's like taking your antenna, dipping it into a wave pool, and seeing the kind of waves that come out of it. And as with polarization, the wavefront has that, it's encoding that polarization, right? So if it's going this way, the wavefront will be coded that way. That way, if I put it this way, the waves will be encoded, that way. So that what you're really dealing with in polarization with radio waves is the shape of the wavefront, right? It's not an individual little thing like I'm saying a photon is. It's going to be my analogy is like if you're at the beach and you see the waves crashing onto the shore, you can see that there's this long line that represents the wave coming on shore, right? And that is how the wave in space for a radio wave looks like, right? And the polarization would be like if you're a ship And if you're a ship, you know that if there's a wave coming at you, you don't want to be broadside to the wave because the whole wave will hit your ship and capsize you. So that would be like a polarization where you get the maximum amount of energy. That if what you want to do is you want to point your ship in the 90-degree direction of the wave so that you get the least amount of energy, right? So that's a bulk example of how a ship aligns itself against the polarization of the waves so that it receives the least amount of energy. And you can see how polarization itself works with the wave concept, right? This is in like stark contrast to the mainstream where they show, that those individual waves at 90-degree angles. It's not that at all. I mean, it's this big, giant compression wave, which it has some length to it, right? It's not, you can't describe it by two sinusoidal lines stuck together at 90 degrees. It just doesn't work that way. But that is a radio wave, and a radio wave is getting generated, I would say. I mean, if you look at what a radio wave is, you have your metal, all you're doing is changing the voltage. That's electron pressure. So the way I see it is that the electrons on the exterior of the antenna are feeling this extra electron pressure coming in from the driving circuit, and that causes those electrons to literally pop out of the antenna surface. So literally, if you were looking at this with a super great microscope, you would see the electrons, the exterior electrons, actually, poke out and return back into the metal. You'd see it do that. You'd see something actually physically waving in space, right? You see these electrons popping in and out of the surface. So the question is that, getting back to the question, is that those electrons are sitting there and they are impacting something. There has to be some medium which carries the waves. So when you're generating a radio signal, we're just causing the surface to literally expand, and that is pushing against whatever the medium is in space. And then that creates a compression wave, and then that compression wave leaves, and that is what the radio wave is, a compression wave. No electrical field leaves the antenna. No magnetic field leaves the antenna. The only thing that I'm saying is leaving the antenna is a compression of whatever the medium is, right? And of course, the big question is, if there's a medium, if there's a wave, then what's the medium? So that's the next question we'll get to, if there is a wave, what is the medium? Okay, so very good question, because unfortunately, mainstream crimes has never been able to find this medium. So why should you believe anything I'm saying, right? Okay, I'm going to put another line in the sand, and I'm going to tell you what I think the medium is. All right. Now, the medium could be anything. A lot of this distance science will just say, it's this ball, it's this fundamental particle, it's a circulon, whatever it is, just put EON on it, and that's what we'll call the medium, right? Unfortunately, the problem with doing that is that no one can ever prove that that particle exists, because apparently it doesn't have any relationship to any of the known particles, electrons, neutrons, neutrinos, quarks, whatever. We found we have some evidence for those things existing, but if you're going to just make up a medium, well, you can do that, but I prefer not to. I prefer to think that, well, if there is something out, even vacuum space, if we think there is something out there, then what could it be? Now, I would prefer to use some of the particles that mainstream science has found. So what do we got? We've got neutrinos, we've got neutrons, we've got electrons, we've got positrons, protons, and a whole bunch of particles. Got the Higgs boson. There's like this zoo of particles you could possibly choose from for a medium. But unfortunately, all that zoo, none of them are stable, right? This is why I think, why do they think there's, a Higgs boson, they made this thing that only lasts like 0.000 microseconds, right? If space were made out of that, it would have disappeared already, right? Because, it decays. So space clearly cannot be made out of something that decays, I don't think, right? So that gets rid of most of the particles. That leaves us with like, protons, electrons, positrons, maybe neutrons. Neutrons are kind of stable, but not really. So let's stick with those ones. So like Dirac suggested that it's an electron sea, right? That's what he proposed. Unfortunately, I think because of the negative charge of the electron, we could clearly tell that that thing exists. If you were surrounded by that much negative charge, right, that would just like dwarf any positive available charge, and we would see something totally different than what we'd see. And you would think that we would be able to strip these electrons out of space, and we'd see massive numbers of electrons. And but we don't really see that. Or you could say it's made out of, say, protons. Let's say the entire space is made out of protons, and we kind of have that same problem. That would be massive positive charge. So what we'd really be looking for is something more neutral, right? We are looking for something because we don't measure any net charge in space, pretty much. So we'd be looking for something neutral, right? Now that could be a neutrino, except that we're not exactly sure what neutrinos are. Or it could be neutrons, except that neutrons, generally speaking, only last 15 minutes when they're outside of an atom, but they do last forever if they're inside of an atom. So they don't necessarily decay. So, I mean, those both remain actual candidates for the medium. And but this is what I'm going to say. I'm going to say that the medium does consist of a neutron sea. And neutrons consist of a positron and electron dipole. So that's what I've always that's always been my main shtick. Anyways, if you look at any of my papers, that's what I start with. I start with space being made out of positrons and electrons. Okay, it's not made of some mythical. It's not made out of circulons. It's not made out of FPs. It's not made out of whatever particle you may have made up in your head. I'm saying that it is literally made out of the same stuff as we are, which is electrons and positrons. And in my theory, an electron-positron pair, which I have dubbed the poselectron, is actually the same thing as a neutron. So it really is a neutron. See, the only difference is that a neutron is being ejected from an atom and it has some energy. So it is an EP, electron-positron pair, but it has some kinetic energy against the sea of neutrons. So, but they're basically the same thing, right? It's just a sea of neutral particles. By the time they join together in an electron-positron pair, they are almost completely electrically neutral, and it's very hard to detect. It's very hard to detect neutrons, generally speaking, and neutrons, interact very little with matter. I mean, neutrons can pass through several feet of lead, and as if it wasn't there, right? Now that I have not excluded the possibility that neutrinos are the medium, and that is because I believe that the neutrinos are not actually a physical particle. I mean, near as we can tell, they are massless, and so that is more in line with it being a wave, right? So a neutrino travels through this sea of neutrons or pos electrons, just like the wave that travels through a Newton's cradle. You know, if you've seen these things, you've got the one ball, it hits, it goes through the string of balls, and then it kicks out the other ball at the other end. So we can see that there is definitely some energy being transferred between those string of balls. And I'm saying that what a neutrino is that very specific case where the wave is just a single bump, and it is traveling from particle to particle as a very specific, you know, single wave through a particle, just like, I mean, the only way I can describe it is like the Newton's cradle, or if you line up a bunch of billiard balls in a straight line and you hit one end and it knocks the other one out. And that is opposed to a photon, which I'm still saying is in the shape of a wave. So certain predictions are that, well, probably you can't polarize a stream of neutrinos. Would be one experimental aspect, because that there's no way to encode the polarization in a single spot. So it takes a minimum of, like, you know, if you've got a medium, it would take a minimum of 3 units of your medium or 3 neutrons to encode any kind of direction into that thing. So that's what I have my that's why I'm putting my line in the sand. It's made out of real particles that we recognize, right? Not something mysterious. So let's see, we've got some comments here. Let's take a look at this. Let's see here. Well, we got a lot of comments here. I've been blabbing for quite some time, I guess. See here, I agree. The notion of segment in one direction explains polarization, but I add rotation of the segment at the frequency of color in the plane of polarization. Okay, I'm not exactly sure what that means. I mean, another aspect that I forgot to tell you about, and with respect to polarization, is how it can be done. Now, one of the strange ways of polarization can happen is that if light hits the surface of water, that will polarize the light, right? Now, in this case, you know, you got to ask, well, where's the picket fence? You know, there's no picket fence in a blank lake. You know, you can also do this against a glass surface. That this is all it takes to polarize light is to reflect it off of a reflective surface. Whatever reflects off then becomes polarized. And if you then looked at it with your polarized glasses, then you will find that you don't see that light anymore. And that's how the polarized lenses work. That it filters out things which have been reflected from the ground, basically. Now, the way I see that happening, you know, is that you have your surface here, right? There's just any surface, flat surface, right? Then you have your, like I said, if it's coming in as a rod, then what's going to happen is that if it is directly aligned with the surface of the paper, then the full rod is going to be reflected, right? But if it's like at some different angle, like it comes in like this way, not in the same angle, then what's going to happen is that, you know, that's not going to get reflected, you know. That is going to get partially absorbed, and only a fraction of the light which is aligned with the rod is going to get reflected, right? So, you know, and something coming in a completely the right angle is not going to get reflected at all. This is just the nature of reflective surfaces, right? So, and then in that way, I'm trying to motivate you to see that that is how polarization works against a reflective surface, right? It's going to only fully reflect the rods which are in actual alignment with the surface that it's bouncing off of, right? Has nothing to do with picket fences, has nothing to do with electric waves or radio waves or anything like that. It has to do with the shape, the wave front is the important thing. And I also didn't explain that in terms of reception of radio waves, I mean, actually, the deal is that if you have a grid and you have a grid is pointing this way and your polarization is pointing this way in the same direction, that if you're building a radio polarizer, it turns out that if the polarizer is in the same direction as a transmitter, that is 100% absorption and blocking event. So why is that? You'd think that, if you were thinking ropes through picket fences, that if they were aligned, that would allow that to go right through, right? That's the picket fence. But in reality, in radio waves, if your polarizer is aligned with your transmitter, that's 100% block. And why is that? That's because when the radio wave comes and hits your receiver, it gets the full impact. And what happens is that actually generates a voltage in the receiving wire, and it sucks the energy out, right? When you receive a signal, that act basically absorbs the wave, so it cannot pass. It comes and hits the polarizer, it gets absorbed. Therefore, you don't see it here. But if you transmit it in a 90-degree angle, then it goes bang, and very little bit gets absorbed. It keeps on going, right? So polarizer at 90 degrees to the transmitter, that allows complete transmission, right? So this is actually how polarizers actually work. That they work by like I say, absorption. That if your antenna is aligned with the wavefront of the incoming wave, it absorbs it, converts it into heat, and it is not allowed to pass. So that is also an important aspect of polarization, in that we do actually see that happening. That if you look at how they make polarizers, I mean, literally, you can make a polarizer with a bunch of just thin parallel wires. They call these wire polarizers. And if you look at how they make these polarized glasses, what happens is they take a conductive crystal and they stretch it so that also literally it is like a series of parallel wires, right? And the way that these work, I mean, they do measure it. I mean, the waves get absorbed and are converted into heat, right? It's not like they're getting physically blocked by a picket fence, right? Is that they are waves. The waves get their energy is getting absorbed by the polarizing material and being converted into heat, right? So once again, that is why I keep on going back to the fact that the shape of a photon must be a rod. Or in the case of a radio wave, it's a big, big, long rod. The rod is the length of the transmitter rod itself, right? It's at least that long. It's just like an ocean wave. But a photon is only this little teeny little bit here. So. But that gets to the question of, why is the photon only a tiny little quanta versus radio wave, which is this big, long ocean wave thing, right? Okay. Now, that has to do with atomic theory. Now, I have a paper on this, so I'm going to share that. Let's see here. I'm going to share my screen here. Okay. Let's see here. That is flashing horribly. I don't know what's going on there. That did not happen before. let me see if I can get that, fix that up. Did you guys see that flashing? That was terrible. But I am going to, let's see here, put a link on here. So that's a link to my paper there. Let me see if I can do this again without it flashing crazy. I'm going to just share my entire screen here. Okay, there we go. All right, now the conventional picture of light generation is that we have the central atom here, and we have electrons which are orbiting at some distance from the nucleus. And so we have n equals 1, it's very close, n equals 2, it's further away, n equals 3 is really far away. So we have these mysterious orbits which get further and further and like exponentially further away, right? In order to generate these light waves. Now, I'm going to take a radical departure from this. I'm saying that that is not the case. I mean, why would electrons be orbiting at these distances anyways, right? How would they know how to stay there, right? There's no explanation for this, really. It's just, if you think about it, it makes no sense at all. So this is why you have to actually, in order to explain how light is generated, is to completely rewrite the atomic structure. And the way that I do that is I say that all of the electrons, when they're in the ground state, they're not excited, they do in fact all fall back into the nucleus, right? Which is what everyone in electrodynamics predict they would do. If you put an electron around a nucleus, it should radiate, it should fall right back down, done, right? And so that's what I basically said. That, if you had a proton and an electron, what's the electron going to do? Is it going to sit there and orbit the proton? No, it's just going to go fall right back down to bound, and it's going to be stuck together like two magnets. That is what an electron is going to do by every known law of physics. That is what an electron is going to want to do due to the attraction of the Coulomb's law of force. It's just going to want to stick to the proton and not orbit. So if it's just stuck on the proton and not orbiting, then what is generating the quantized light? So this is what I say. Now I say, since space is filled with this, positron / neutron sea at every point, I mean, it's like a glass of water, completely filled, right? There's basically no spaces between the water molecules, and there's basically no spaces between the pos-electron particles, which means that in order for an electron to move, it actually has to push another particle out of the way. And so what this effectively does is that it quantizes space like it's a graph paper. So I've shown space here basically like a graph paper where every single slot is occupied by some particle, right? In order to get the electron, like if it's stuck against the proton here, so this is a simple hydrogen, so that's proton. In order for the electron to move away from the proton, it has to shove a positive electron out of the way, and that causes it to move a fixed distance. And in order to move even further, it also has to move yet another quanta of fixed distance. So it's like, at this level, the world is like a Lego brick plate, where you can put the brick here, you can only put the brick there. You can't put it halfway between the studs. It has to go a quantized distance away from any other object. You cannot take arbitrary distances away. But it's only a single step, right? All of these steps are all evenly spaced. I mean, unlike conventional, where you have to go, well, the first one is really close, and the second one is further away, and the third one is really far away. Why would they do that? All we're thinking about is the electron is going from one step to one step to one step to one step. Same distance steps. Now, if you look at the Rydberg formula, which I have here, if you're familiar with the Rydberg formula, the frequency of the light that is generated is this Rydberg constant, which is 1 over n squared, and 1 minus 1 over n squared 2. Now, this 1 over n squared thing should look pretty familiar. That is Coulomb's law, right? That's all that is. And the n represents the distance. So n equals 1, n equals 2, n equals 3. So all you're doing is that it turns out the frequency of light emitted is just the difference between how far the electron moved from one slot to another. So if it moves from 3 to 1, then you just plug that into the Rydberg formula, and voila, you get the frequency of the light that's emitted. So what we're looking at is just like the release of potential energy. It's just like if I had a bowling ball, but instead of being able to lift it smoothly, that I could only lift it at like 1 foot increments. So it could only be 1 foot off the ground, 2 foot off the ground, 3 foot off the ground, 5 feet off the ground. And when I drop the bowling ball at 5 feet, yeah, it hits the ground, releases energy, you hear a big boom. That is what's happening when light is being generated. You've got something like a bowling ball, it's falling through quantized levels, right? And there is also other experimental evidence that suggests that space is actually quantized in this manner. That I would cite the experiments where they basically drop neutrons and they see basically where it hits after they bounce. And they find that they don't just hit in any possible place. They only hit very quantized areas, showing that the neutron is not free to travel in any way it wants. That it has to, at some point, the world gets like Lego brickish, and it can only move in quantized steps. So this explains, how light is generated, in that it's just like two objects coming together, just like my hands slapped together. That generated a very sharp sound wave, right? If you were to look at the oscilloscope, you see this big spike. That's it. So it's a physical process that the electron generates light by actually hitting the nucleus, or the proton in this case. And it generates a quanta of light. Now, but if it's a quanta, then what exactly do we mean by, say frequency and amplitude? So the other thing that I'm saying about a rod is that, well, how can a rod have an amplitude and actually a frequency, I would guess. And the way I kind of explain it is that it's kind of taking a tennis ball and throwing it in a box. So if you threw it kind of slow, it would go boom, boom. But if you threw it really fast, you go boom. It would bounce back and forth really fast. So what you would see is that the amount of time for each of those little waves, it would be basically shorter. Although even in my mind, I still have a hard time figuring out what that is. But one thing that I think we do know is that the amplitude of these waves, if it's in the shape of a rod, like it's going down a trough, the amplitude, which is wave height, I believe is going to, in fact, be constant. And we see that in this formula here. It says energy equals HV. So what does that mean? That means that you have your V, which is your frequency here, and multiplied by some constant. Okay, so this just means that every single wave there has this fixed amount of energy. And the only reason why the energy is higher is because they come more frequently, right? So, let's just say we deliver like 1 joule of energy per second. And actually this energy here is actually the total amount of energy in joules that is received over a full second, right? It's not the energy of a single wave in the photon stream. The energy of a single wave is actually this H. And the V represents how many of those you get per second. So if you get 10 of these per second, then you're going to receive 10 times as much energy. So this gets into a discussion of, say, the photoelectric effect. And this is one of the reasons why they think that, light is a particle, right? Because it appears to contain a quantized amount of energy that cannot readily be explained by waves, because they're figuring, well, if light was a wave, then if I increase the amplitude, then I should be able to eject electrons at basically any frequency, right? Because I can make the amplitude as big as I want, right? So they just turn up the light source thinking that they're increasing the amplitude. And that doesn't work. So you have to have a certain minimum frequency in order to actually eject an electron from a metal. Now, the problem here is that they're thinking that by increasing the brightness with their control knob, that they are increasing the amplitude of the wave, but they're not. Okay, you can increase the brightness, but all you're doing is increasing the number of those rod-like particles which are being emitted by whatever you're doing the emitting with. But they still have the same amplitude. So no matter how many, let's see here. Yeah, they're not changing the amplitude. They're only changing the just the quantity, I would say. Although, like I said, this is getting kind of one of these areas where maybe I'm not thinking quite straight. But what you have to do is that when you have to increase the frequency, which is the number of particles impacting per second, right? So it's like you're taking a nut and you're trying to shake it off the tree, and it's like if you just go like this, there's just no matter how many times you do that, you're just not going to have enough energy to shake the nut off. You have to increase number of shakes in order to input enough energy into that connection to cause it to break, right? But any bit of energy that you stick in is still just the same, right? The amount that you can wave the branch at is fixed. And this is why you can explain this photoelectric effect as still basically a wave. And the thing that is being quantized is the amplitude. And that, this formula here is really telling you exactly that each wavelet only contains a fixed amount of energy. If you want more energy, you have to send more of them per second in order to work. So I do have another paper here. So if you're interested in seeing my my papers, I do have them all here. And I have a little video introduction. And one of my more popular papers is explaining basically how spectra work on larger atoms. So now you'd think that we have a lot of sophistication about how it generates spectra, but it turns out all of that stuff only works on hydrogen, right? That Rydberg formula thing, that only works on hydrogen. You go to either even helium or lithium, that stuff stops working, right? We basically don't have a very good way of predicting, what is the spectra of, say, carbon, right? It's we don't have any formulas like that. But if what I'm saying is correct, and that the spectra is just being generated by electrons just taking fixed incremental leaps away from the nucleus, then you would think that any spectra should be explainable in terms of these Rydberg-like formulas, where you just have 1 over n squared minus 1 over n squared kind of thing. And basically, that's what I found was true, that you can go and you can find patterns in the spectra that explain how these things are generated, right? So, and it's just a matter of arranging the data so that you can see that, right? So I arranged the data for, like, we have the hydrogen spectra here, and you arrange it by putting the wavelength in nanometers against the number n here, right? And so instead of the spectra, I mean, if you ever seen the spectra of hydrogen, it's just like, it looks like these randomly spaced lines, right? It doesn't look like there's a pattern to it at all. But if you arrange it, then you'll see that the spectra does take on this very specific stair-step arrangement, right? So that's like finding patterns. And that's what science does. We find patterns in the data. Now, you can find patterns like that in helium. So the Rydberg formula also works for if you ionize off one electron and then effectively make it a 1 electron atom. So helium also follows this pattern, which is actually can be expressed as being a combination of 2 Rydberg formulas. And so here I made like a calculation showing, you know, how accurate this idea is. So I came up with a formula for the spectra of helium and measure, you know, what the differences are. And it's pretty close, you know, it's not 100%, you know, probably this wouldn't pass muster in most places, but it's pretty close. And we can also do this same trick on lithium. We can still see this stair-step pattern here, and we can still account for most of the observed lines in lithium. I mean, the formulas are pretty complicated. I mean, they kind of look like this, right? This n to the cube times 1,000 divided by n minus 1. But they are there. And I kind of, you know, you kind of have to do a fitting to do this. So not exactly rigorous, but you know, even beryllium, which is a really big atom, if you look at the spectrum beryllium, it looks totally random, but you can plot it such that it does reflect this same pattern. So that is just one motivation behind, you know, why whether this could be true, that electrons are not orbiting the atom, that they are just taking the steps away from the atom. And you know, you do have to compensate for the different electromagnetic strength because there are still other electrons in there. But it's not this super complicated multi-body problem that mainstream makes it out to be. So let's see here. So we got some more comments here. As we get comments about neutrinos. The neutrinos are the passage of energy to top and bottom. Well, I don't know which top and bottom you would be talking about. Let me see what other, we got a lot of comments from Espacio here. But they're all kind of like this, right? As you know, the watermelon gets its energy from the middle, so does Earth and all planets from the disk. Not quite sure what this has to do with photons here. But we have a comment from Roger. It says, no, force obeys force curve of Boscovich. Newtonian physics updated in 18th century. See, is that the one where forces are like attractive at some distance and then repelling at another, and then attractive at another? And so we haven't even gotten to forces yet, I don't think. Let's see here. Let's see here. And now we're talking about gravity. It must be acted by a push up force, push down force. Yeah, so there are a lot of comments by Espacio, but I am not exactly sure how to respond to those. But let's see here. Well, we've got some people in the green room here. So I think I have pretty much covered what I wanted to cover, which is, let me just summarize here. And then we're just going to open it up for chat and comments. So I am saying that the shape of the photon, it's a rod, all right? And a rod in the sense that it's a rod-shaped wave, right? It's still a compression and rarefication phenomenon. So a photon is not a particle. It does not travel from point A to B as a material object. It travels from point A to B as a compression wave, and the particles themselves don't move. But I would say that the reactions that we do see, like when a light hits a solar cell, that's because the wave is pushing actual particles into the material. It is like a collision of particles, right? The actual work is done by particles, just like a wave hitting a ship. The work is done by the particles constituting the pressure of the wave, right? The wave itself doesn't directly interact with objects, and that the rod has an orientation. It comes out and it has orientation. It has an orientation in the transverse direction. That determines the polarization. And I explained how polarization works, and that polarization kind of works a little bit differently between radio waves, which have these big gigantic waves the size of the original transmitting antenna, versus photons, which are generated by atomic processes caused by electrons going a fixed integer distance away from the atom. So that's it. That is the shape of the photon. So if I see you have some people, we always have Ian. So Ian, you don't mind if I bring you up here? Let's see here. So Ian, you've been listening a while here. So what do you think? Could the shape of the photon really be a rod, or do you think that's just crazy?
Well, Franklin, I mean, it's most interesting, the complete exposition. It's certainly interesting, but I could put it back to you a little, if I may. I mean, I have an open mind about this. It's an interesting model, but I mean, you earlier on required very direct experimental evidence to substantiate what is a useful model of the electromagnetic radiation wave. Electromagnetic radiation. You wanted to be able to measure very precisely the electric properties and the magnetic properties, rather than say indirectly how electric fields and magnetic fields affect the wave. So I could put it back to you. I could say that, you know, your model is very interesting and you've tried to explain a lot of things, but I'd require direct experimental observation of, say, this rod-like photon, rather than it being a sort of a circular type particle or something like that. And I don't think that exists. You've got a model to try to explain your understanding of polarization and your understanding of the transition of electrons giving rise to radiation and so on. But you've nothing direct. I mean, if I may say so, Franklin, we frequently, all of us, we correctly, and I think James Keane has been doing it here in the email, we correctly criticize the direct mathematician who is just fiddling away with equations and not having cognizance of the physical situation until he wants to verify his theory. And then he does that at a very late stage. Well, perhaps you're doing it in the opposite way. You're looking at physical models and so on, but there's nothing direct to substantiate that your models are correct. Now, I'm not saying they're incorrect, but I'm also not saying I'm convinced.
Yeah, I think that's very important. I mean, I would be called like a theoretical physicist. I mean, I just come up with things in my head. It's up to the experimentalists to determine whether these things are true. So, and I'm saying that, well, given the mainstream theory, the experimentalists have not done their job. And you're right that if I think that light is in the form of a rod, then what I need to do is I need to convince some experimentalists, because that has some very specific physical meaning. Like if it has a rod, then it has a width. Specifically a width. Experimentally, you think someone should be able to make some clever experiment that say, that is for a photon like 0.00 something meters long, right? There should be some experiment where you kind of spray electrons onto a detector, and what the width of the detector, and if these photons are of a fixed length, then you predict that as you sweep something across or something like that, that you could actually determine the length and the orientation of that photon, right? And this is where the theory is important, because, I might not be clever enough to design an experiment to directly detect that. But I'm telling the experimentalist, you're looking for something like this, right? You're looking for something like that. And experimentalists will go, well, I know we have this kind of things and this kind of thing and this kind of thing. They may actually be able to go out and actually find that and say that, yep, that's what it is. It's not an electric field. It's not a magnetic field. It's actually, it would have to do something along polarization or something like that, that would help confirm that it is, in fact, that it's a wave and it's, in fact, that shape. So, yeah, I think that, you're right. And that, this is a theory that I came up with within, I don't know, like the past 2 or 3 months. And this is kind of like, I've been kind of mentioning it, but this is kind of its first kind of public presentation. So I took the chance that I've been wanting to go and explain this, what I think is a major discovery. It's as big as like the DNA helix structure. Although it's not that exciting because it's just a rod, right? It's not some exotic shape. It's not a helix, not a vortex. It's just almost the simplest shape you could think of, right? It's a stupid rod. So, but for example, what did you think about the ideas about how light is generated? That it's generated because an electron is taking this fixed step away from the atom, and it's not this ever increasing, orbits around the atom.
Well, I thought again that was maybe not an unreasonable model to take, but I'd require direct evidence that is superior to the existing maybe models. But one other thing that it occurred to me as you were speaking, and maybe we've broached this before, is that you talked about the photoelectric effect, and you talked about the photon, if you like, being a sort of a wave and so on, and the surrounding areas being affected and so on. But you seemed and you seem, because I've discussed this with you before, you seem to be somewhat dismissive of a sort of an ether and the properties thereof, which I would have thought would fit in with your system, because you're talking about the surrounding areas of the photon being subject, the fan particles, if you like, being subject to some sort of wave pressure in the same way as a water wave would be. And therefore, I would have thought that you would have something to say about the medium, about a medium, in the same way as one would have a water as the medium for the water wave transmission. But you either don't say anything about that, or maybe you dismiss it. I don't know if I'm being unfair there.
Oh, I'm not quite sure I understand, because I'm total etherist, right? I say that, yeah, every phenomenon can be explained basically hydrodynamically. And any question you have about my medium, you can basically answer it by, well, what does it do in water or air? I mean, other than the fact that the medium is a superfluid, which doesn't have any losses. See, that's where the disconnect is. So as long as you're talking about phenomena that don't require a friction-free, like the waves, like if you talk about, well, what does a wave, then I say go look at water. And what is a wave in water? It's just a compression of the H2O molecules and a decompression, right? But then if you ask me, well, then why does the wave go forever, right? Because we don't see that in a water wave. A water wave definitely slows down and stops at a fixed distance, and light just goes forever. Once again, that is a difference between that is something that requires the superfluidity, frictionless, non-dispersive properties of the ether. So most things can be explained in terms of well, why would you think that I don't support, say, the ether mug? Did I say something on that?
No, I probably took you up wrongly there, because on that part, I may have been confusing with somebody like Harry Ricker or something, who talks about this thing, but then he dismisses ether. And I'd forgotten that you and I were sort of ad idem in regard to this model. But where I perhaps do differ from you, and I put a statement in the chat earlier about this, is that Glenn Borchardt a couple of weeks ago, he sort of seemed to imply that, well, people are dismissing a tired light, but actually he dismissed the concept of an untired light, or an untired radiation. It might be quite small in comparison with water waves, the dissipation, but there must be some dissipation if there's a medium, a hydrodynamic medium, which we're agreed upon. I wasn't clear of that, but of course I realize that now, and I remember it now. But you maybe dismiss it and say that it's zero. In other words, this thing will go on, which is perpetual motion. So I think we differ in that regard, but not in regard to the hydrodynamic nature of the transmission in the medium.
Well, I think that would just be a matter of, say, magnitude, because generally speaking, it has no losses. But at astronomical galactic distances, you think that, yeah, I mean, it is a wave through a medium. It can't. You'd think there'd be some losses, even from it just running into junk along the way, I guess. And that's how I see light when traveling extremely long galactic distances. What happens is that basically its speed is not 100% the speed of light. It actually, the wave actually, if it's like 5 waves, it actually stretches out. Frequency decreases and it gets longer, to the point where it actually at some point disappears. And so that's where I think the redshift actually happens across astronomical distances. That it's tired light, but it's getting tired in the sense that its wave packet is just spreading out. It's just physically getting longer and longer. The amplitude and the frequency is decreasing until it becomes nothing. And that's why we see redshift, not because, and this is where I disagree with like all this expanding universe stuff. It's like, I kind of disagree with that. Like Obert's paradox says that Now, if what I said is true, which is that a photon of light can travel absolutely freaking forever, then you would think that if the universe is infinite, then it says that when we look at in the night sky, it should be as bright as the sun, because there's got to be a sun at every single spot in the sky. It's got to be sending a full volume photon at us all the time, and so it should be looking at we shouldn't see dark sky. So I would say we see dark sky because the light from all those suns gets redshifted to the point, and this is where I explain where the CMBR comes from. All that is just all of that redshifted light from the extremely distant suns, and this is why it comes in as black body radiation. What is black body radiation? It's the same thing that happens when you heat up a steel bolt, and it has this pattern, right? It's the same thing that comes out of sun. Sun is a very good black body radiator. So if you take all of the black body radiators and just redshift them because of this expanding waves, then you eventually get what we observe as a CMBR. And what we're looking at when we look at the CMBR is actually the pattern of stars that are surrounded. That's why it's patchy. That's why it looks just like our local galaxy. If you look at our local galaxy, it's patchy like that, right? There's clumps, there's dark spots, there's bright spots. It's not even. So that's what I believe we are actually observing. And I personally think, even though I have no specific evidence, that I think that the universe is in fact infinite, and it's always been here, always will be here. I'm just waiting for them to put up the James Webb telescope, because what they're going to find is that, oh, well, the universe is not 16 billion years, because now we can look out back in the infrared and we can see all these other things that are 23 billion years old. So I guess we got to push back the age of the universe back to 23 billion years. And then when they get the next better telescope, they're going to have to push it back to 100 billion years. And when they get the next, they'll finally get to the point where they decide, oh, well, the universe is infinitely old.
Well, they might invent more dark energy and more expansion criteria and things like that to save the existing theories, of course, as you well know. So I perhaps am a little skeptical about that happening, but obviously it would be nice to have the data. But by the way, have you done any calculations about the CMBR, like to find the temperature, like 2.7 Kelvin or something, rather than any other value?
No, but I just basically match the. I'm saying that the CMBR is what it is. It's just given our position in the galaxy. I would predict you see black body radiation, and that's exactly what we see. Anything less than that probably goes below what we can generally detect. And it's very small. I mean, it's kind of like.
Okay, well, thanks very much. I really want to ask things. Perhaps I should let somebody else in now. But thank you for the presentation anyway, Franklin. And welcome back. I mean, David obviously was a breath of fresh air, but all the same, welcome back to the sessions.
Yeah, I thought that was good because we weren't able to have a conference this year. So with David bringing in all those speakers, I think, we kind of got our conference, I think. We had a lot of interesting speakers on a lot of different topics. And so it was great that David could arrange things. I would like to arrange that too. So if there's people out there who want to present, please contact us. I just don't have as much pull as David has to, bring in speakers like that. This talk here is more in the vein of what Glenn Baxter did, which is to just bring together a small group of people to just randomly discuss whatever was happening be on their mind, like it was a coffee conversation. And that's.
Well, maybe I'll just say a word which you might care to think about, Franklin. Just what I've been doing maybe over the last 9 months or something, 6 to 9 months. I've been working somewhat with Dennis Allen. I'm not sure if he's here today, but on analyzing the work of J.P. Wesley, rather, John Paul Wesley. Don't know if you've heard of him, but he's an American dissident physicist who died in 2002. He emigrated to Germany before he died, and I think his widow is living there. But anyway, one of the books that he's produced, sort of self-published, is called Scientific Physics. And it's quite theoretical, actually, but it covers all the areas we've been talking about and the things you've just mentioned now. So we're analyzing that, and we're accepting a lot of what he's saying, but we're trying to maybe correct it. One of the things he analyzes, he says that transverse electromagnetic radiation is only part of the question. And he does a similar analysis to the sort of Maxwellian analysis for that, for longitudinal radiation, which he calls normal radiation. So we think he might have made some inaccuracies there, but we're looking at that. Now, that's one thing that's ongoing at the moment. The other thing is that I did a little more analysis on the behavior of interferometers in a sort of an MMX type situation, which are moving oblique to the ether wind. So in other words, not directly in the same area. And I've published a small paper, which I rather than put up on IXRA, which perhaps I should have, but I've submitted it to Galilean Electrodynamics. I think they're looking at it at the moment. But one of the things that comes, it was to analyze some work which is done by this Wesley character, this J.P. Wesley. And we think he's made an inaccuracy in looking at this subject. But anyway, I've tried to look at this. But one of the things that perhaps comes out of it indirectly is that you get a sort of a very slight sinusoidal variation with orientation. Like when the interferometer is in the same direction as the ether flow, let's say. And perhaps what we're measuring here is the effect due to the flow against the ether not being carried by the Earth in its rotation, because the experiments seem to show that it's more or less damped out in its revolution. It's like carried in this bubble, as we've called it before. But at zero you get the maximum value, and then it's a difference between 0 and 90 degrees. And then at 45 degrees you get nothing really, because the difference cancels out. And then at 180 degrees you get the same, but in the opposite sense. So you get a sort of a 2 theta signature in that. Now, if you look at that, you get a sort of a very slight sinusoid with the period 180 degrees. And my formula works that out. And I believe that it's probably more correct than the formula Wesley worked out. But if you look at the original Michelson-Morley experiment in 1887, and where the thing was being rotated like by 30 degrees, and they did the experiment and they rotated by another 30 degrees, you get a very slight sinusoid. And it appears to be the period is about 180 degrees. So I just thought I'd tell you that. And if you want to talk to me more about that, or I could give a short presentation at some time if you want me to do that.
Okay. Now, I also see we've got a lot of comments from James here. So James is also here in the green room. So James, I'm going to bring you up, and let's just talk about, you have a number of comments here. Let's see.
Well, one thing in my comments that is emphasized is the need to have some mathematical definition of all of these terms that we're using, so that different people can understand what they actually refer to, or provide alternatives. A second thing, which is not in my comments, which it occurred to me, Franklin, that your cylinder concept of is it the photon or the wave? I don't know, but your cylinder concept does have a mathematical formula in Euclidean geometry, right? Of just a cylinder, right? You can calculate its volume, its length, its the radius of a spherical cross section of the rod, right? So what I'm saying, wondering is if you might consider, Franklin, you mentioned that depending upon the polarization or the angle, with which the rod hits the antenna, whether it's parallel or perpendicular, as you showed with the two pens, the amount of signal captured is reduced if it's perpendicular and not parallel, if I understood what you were saying.
Yeah.
Well, if there's great, if there's actual data on this point, it could be you could fit what length and radius of the rod actually is that would fit the data that's actually observed, and thereby perhaps provide some sort of support to your model.
Yeah, we were discussing that. I discussed that with
Okay.
Ian. Someone should be able to, given the hypothesis, and that's what science do. You have a hypothesis, and then you say, if that's true, then we should be able to build this kind of radio receiver, and we should see this kind of result. Is ultimately what needs to be done.
Well, I'm
believe
being very specific here. What if you had the plot of the intensity of the signal received based upon the polarization, whether your rod is parallel to the antenna or at 90 degrees, as you pointed out. Oh, okay. So you've got that curve. That's data. Somebody must have measured that at some point. Well, you could ask your question: what radius of let's say the rod is going to be the length of the antenna. So we take out one parameter. The only other parameter is the radius of a cylindrical cross section of the rod. Am I correct there? If so,
yeah, correct.
What radius would the rod have to be to fit with the data? I would be interested as all get out to hear that number. It is probably, if you have the data on the drop in intensity as the polarization changes from zero, parallel to 90 degrees. If you have that data, I would think you could almost fit what radius of your rod model, what that radius must be to fit that data. I would love to hear that number.
Yeah, I think that's true. I hadn't thought about that, but yeah.
Yeah. Okay. Hey, good. Good.
I mean, we know physically
I really like that.
wide the receiving wire would be. I mean, even in polarizing lenses, we have some idea molecularly how big that thing is.
It would seem to me that there has to be only one radius which would fit that data. So what is that radius? That would be, and perhaps a way to further your model as a theory.
Yes, the experimentalists out there, there's something to look for. And I assure you, if you can prove this, you will earn a Nobel Prize, right? Because this would
but I'm not talking about some experimentalists. You already have the data. Don't we have, presumably, I understood from what you said that we have the data as to the signal intensity being maximal like this and being minimal like this. So did I misunderstand that we don't yet have that data?
Like that. There might be, or because no one specifically looks at, what is the fractional remnant when you're at 100% block polarization, which is what we'd be looking at. We'd look at when you're totally black, something is still getting through. What is the
well, presumably there's a curve there
that it's blocking,
measured in lumens or whatever measure of intensity you're going to have.
Ultimately, I want to say that my rod is like this long in meters. What I want to say, and it's got to be that length. And that if I use different kinds of light, I would find that it's the same. That kind of thing.
Oh, okay. But if we have the data or a theoretical plot of what full polarization from 100% transmission to perhaps 0% at the 90-degree angle, is that a linear curve there, or is it a function of angle? What is that curve?
I'm not exactly.
What radius? You don't need an experimentalist. What you need to do is to get out your laptop and say, what rate? Let's start with a rod the same length as the antenna. Great. There's only one other parameter, the radius of the rod. So what radius must the rod be in order to get that data, to get that curve?
That's a possibility.
You don't need anybody to go into a lab. You need just somebody with a laptop.
Well, no, all those things will differ depending on the materials, the width of the wires, the frequency that's being used. I mean, there are a lot of different parameters.
Okay, so it's not as simple as I'm imagining. Okay.
I think some experimentalists could still do it, but it's still theoretically you still have to model the actual physical wave and then try and predict, how much energy is present per unit length of that wave, and then see how much of it was absorbed by the polarizer and how much was allowed, and then come up with, like I said, the physical shape. That's what we're really talking about here, is the physical shape of the electromagnetic wave, whether it be radio wave or a photon. And in the case of a photon, it should be a very short little thing versus radio wave, which should register as a big long thing. And you could do an experiment just to tease out that difference.
Okay, well, perhaps the premise of my comment was in error, because I thought we had that data already.
No, I don't think so. You'd have to come up with made. I mean, I'd have to work on the theoretical hypothesis to the point where it became something testable. I don't think I've done that yet. But people are giving me ideas. Though. I've just heard about that. It's like, yeah, maybe you should be able. But I still think about what would you expect specifically, right? If it actually came to that specific kind of size. Let's see here, and so you did mention math, and I have to admit that math is not my strong point. It's not. I am a theoretical physicist with an emphasis on physical reality. So, like I said, if I can explain things in a billiard table, I would much rather do that than explain it on a blackboard, right? And like I said, I generally I guess suspicious of things that are written on blackboards. I mean, the role of math should be you should have your physical hypothesis. You should be able to use that to make predictions, and then your experimentalist should be able to confirm those as of yet not confirmed predictions, and that's the true way to do math. Because science, because a lot of dissidents will just match existing experiments with their theory, and that's okay. But anybody can do that. Anyone can modify their theory to match any experimental thing. But I'm saying, I'm saying the light is a rod, right? So there should be some experiment that has not yet been done that can tease out that particular aspect of the photon. And that cannot be explained by this whole electromagnetic, the conventional explanation for how waves work. And that would blow. If this is true, that would just this is as big a difference as Earth is the center of the universe. So I'm saying the electromagnetic wave has nothing to do with electric or magnetic fields. It cannot be more radical than that, right? But yeah, to your point that not very. This is what you do the experiment that you're suggesting. I would have to get deep into the math. I would have to model all this stuff, say this is this wide, and get into the math. But that's where things happen here. Let's see here. Let's see. If, as alleged, that no one has detected an electric component in EM waves, why do radios work? Obviously, this component can be detected. Well, I would argue that what we're detecting is that we're just detecting ultimately a voltage coming out of our receiving antenna. Now, that doesn't mean that it got there because there was any kind of electric field around the antenna. All we know is that there's this transmitter, there's this receiver, and there's electricity coming out of the end of the receiver. But, we have this exact same thing happening with sound waves, and that I speak, we have a microphone, and out the end of the microphone is coming electricity. So does that mean that my voice was made out of electricity? No, it doesn't. It doesn't mean that at all.
You are one very clever man, Franklin.
It doesn't mean that my voice had anything to do with electric or magnetic fields. All we know is that the receiver, there's some electricity. And now I would say how radio works, it works just like a wave hitting the antenna, and it is pushing in the reverse process, pushing in the electrons in the receiving antenna. That pushing electrons at higher voltage, right? So that is how the voltage is generated. It's not, the mainstream is saying it's an induction process, whereby there's this magnetic field collapses, that collapsing magnetic field generates EMF in the rod. That's how they explain it. But unfortunately, if you probe the area around an antenna, there's no collapsing magnetic field there. There's no collapsing electric field there. There is no detectable field at all. But yet we see the voltage increase inside the body of the antenna. And I'm saying that that's a direct push. Physical, direct push. Nothing to do with induction. So, but that's a good question. Let's see here. We've got a few last comments here. Let's see before we end here. Jim said, if there is an ether, then there are no photons. Well, I would say that there is ether and there are photons, but those photons are in the shape of a rod, which is a wave, right? So there's no photons in the sense that they're particles, right? That's what I'm saying. They are not particles, not in the sense like they're a hard little ball or have mass or anything like an electron, but they do have certain properties of particles, but they are strictly waves. So this is kind of a definitional thing. It's like, yeah, there are photons, but photons are different from radio waves. Photons have quantized energy, and that's how I'd answer that. Let's see here. Okay, so I'm just looking to see if we have any other interesting comments here. And nope, I think we've just about covered it. And we have gone through our 2 hours. So once again, this is Franklin Hu. Our topic has been the shape of the photon. And I have put my line in the sand and saying that this is what it would look like. And like I said, I'm saying it's a rod, but once again, it's a wave, and a wave really isn't a rod. It's more like a wave going down a trough, a single wave, just like a wave pool would do, right? It's just a concentration of some material in a certain bounded area. But that's my idea, and thanks for everyone listening. If you have any questions, comments, send me an email. FranklinWho@yahoo.com is my email address. And I love it when people send me any questions. I try to get to all your questions, and they help me think. So one of my main complaints is I have all these theories, but no one cares. So don't be afraid to send me an email message. Or if you have any future topics you would like to speak on, your favorite pet theory is welcome here at the John Chappell Natural Philosophy Society. That's what we do. And we won't make fun of you because you're a dissident. We'll make fun of you because your theory doesn't make any sense. But if you're looking for some people to discuss it, that's what we're here for. All right. So long, and we'll see you here next week then. So I believe we'll be taking back over the normal science chat. So once again, welcome everyone else who joined us from Dissident Science. Please join us again. Please keep on commenting and tell your friends. So, thank you.